Hello, everyone, and welcome to yet another talk in our AISC Literature Survey series. I hope you have been enjoying these sessions. Today, our session will be on ML for interpretability in ML. Our speaker today is Ali El Sharif, who is joining us all the way from Windsor, Ontario, who is doing a PhD in ML interpretability from Nova Southeastern University. Over to Ali for what I'm sure will be an exciting and engaging session.
Thank you, Suhas, for that introduction. I appreciate it, and I look forward to sharing this presentation with everybody that's with us today. I am going to start by, Suhas, you took care of the introduction. Thank you very much. And I'll just note that this is the first of a series of talks that will be focused on machine learning interpretability through AISC. And we just look forward to setting a foundation with the literature survey, going over concepts that are discussed in the machine learning literature. And then with subsequent talks, we would go in and dig a little bit deeper into them. So I'll start with why is machine learning interpretability important? And this is what I'm showing here is a list of decisions that are increasingly being, machine learning is increasingly being used to support. And these are consequential decisions. Should I receive a medical treatment? Will this bank approve my mortgage? Will my child be admitted to a college? Or will I be targeted for a political campaign? And absent of an explanation, many of us would have an issue accepting or some of these decisions being made if we're not happy with the outcome. So the first question is, why can't we rely on accuracy and confidence in the prediction? If I can come up with an accurate prediction that, yes, if you take this medication, you're going to be better, and I'm really confident in my answer, why isn't that good enough? And I'm going to set the context by an example from the literature that's widely cited by the author Rich Corona. And in that particular example, the author was trying to predict the risk for pneumonia patients, and trying to classify them. Are they high risk or low risk? And low risk patients are typically sent home. There's no minimal treatment. High risk patients for pneumonia disease, that's an actual serious case when 10% of these patients typically perish. And one of the findings from that study is the neural network algorithm that was at the time considered not interpretable, not explainable, identified that pneumonia patients with a history of asthma had a lower probability of death, which was attributed later on to the fact that these pneumonia patients with asthma had increased medical intervention. And absent of that context and absent of that understanding of why these patients had a lower probability of death, this black box algorithm, so to speak, could have led to an incorrect or dangerous medical decision. The other aspect of explainability here is what if I'm confident in my answer? What if I have a high level of confidence that my neural network is giving me the right answer? And what I'm citing here in the literature is a study or a paper published under Deep Neural Networks Are Easily Fooled. And what these authors demonstrated that in this case, a guitar and a penguin were correctly identified with 98% and 99% accuracy, but also incorrect images that you can obviously look at and identify that make absolutely no sense for these images to be identified as guitars or penguins. And these images were predicted with a high level of confidence that they are a guitar and a penguin. And you clearly can look at it and see that it's not. On top of that, there are regulatory requirements. If you, in the US, there is the Equal Credit Opportunity Act of 1974, mandating credit agencies to provide the main factors determining a credit score. So if I'm using machine learning to determine a credit score, I have to provide the reason for doing so. And more recently, about 2 years ago, the European Union passed the GDPR with the right to explanation, mandating the right to a meaningful information about the logic involved in an automated decision. So if interpretability is important, it's regulated, why is it so difficult to achieve? And I'm going to provide you with 3 reasons for the reason that why is it a difficult thing to have. Reason number 1, the machine learning methods that we have today are achieving good accuracy and good results, these qualitative metrics, and they're doing so through increased complexity. Think of a neural network with many layers, many relationships, and coming up with these unexpected relationships between the input variables. And by the time we move from these input variables to these output variables, all what happened in the middle is so complex and is so difficult for us to understand. It's the complexity that's giving us these excellent qualitative accuracy metrics. It's also working against us in understanding what happened to get us there. So the natural question comes in, what about decision trees? Why can't we use decision trees to and explainable methods that are fairly simple? Here's a decision tree for classifying animals, and if it has a feather, can it fly? And if it cannot fly, then it's a penguin. Why can't they just use decision trees and just traverse through the path of that tree to have an explainable model, and I can just optimize that? And the answer is this: human reasoning does not scale. Once a decision tree gets beyond a certain level of complexity, by the time you've traversed the bottom of this tree, you have ended up in the same place that you were at with a neural network. Human cognition, there's a budget, there's so much capacity in our brains to process an explanation, and beyond a certain scale, we just can't take it anymore. And then the third reason that I'm going to cite here is the notion of the multiplicity of good models. This was quoted by Patrick Hall and Navdeep Gill, but the original person that coined that term is Leo Breeman, and that is, when you have a convex optimization problem, what you ended up with is an answer that minimizes errors or achieves that objective function, but there could have been multiple paths to get you to that same objective function of minimizing the error. So you could have predicted the same outcome through many different ways, and your explanation of how you got there is could vary depending on the randomness of where you started in a convex optimization problem. So with that said, it's not all doom and gloom. There are positive things and progress that we are making as the machine learning research community to tackle these challenges. And one of the first areas that I'm going to just start with, I'm just going to try to lay the foundation of what is an interpretable explanation that, and I'm going to just start with 2 examples here. So the first is by an organization called FAT-ML. It's Fairness, Accountability, Transparency in Machine Learning. And they defined it as ensuring that an algorithmic decision, as well as any data driving those decisions, can be explained to end users in non-technical terms. Another useful explanation is provided by XAI, provided by DARPA, the agency that brought us the internet. And they defined 6 questions that would just help frame what an interpretability for a machine learning algorithm is. Why did you do that? Why not something else? when do you succeed, when do you fail, when can I trust you, and how do I correct an error? And further, there are unlike quantitative metrics for accuracy, where we have the F1 score, we have sensitivity, specificity. There's well-defined metrics that we all agree on for accuracy. When it comes to interpretability, it's a bit more subjective and a bit more fluid. There's no consensus in the literature today as to a metric for interpretability. So what we're left with is just going in and surveying different characteristics of interpretability and sharing those with us. So I'll share a few here just to give you a feel for what people in our research community have explained. So there is time sensitive, the timing to be aligned with the task. So if I have a machine learning task that's needed to support an immediate decision, if that explanation comes to me a week later, it's not very useful. It needs to be explainable to human, which is aligned with human thinking and expertise. It's mimic human-based reasoning, which is defined in this particular case as the level of agreement with an expert judgment. And you can just imagine how we could design some studies around having the machine learning algorithm come up with a prediction and a reason, having an expert do the same, and then comparing the two and identifying the level of agreement between the two. Support case-based reasoning. In the context of similar cases, sparsity, the ability to select a subset of features that are important in the decision, and then understanding feature contributions to the final decision. And I'll just keep going, and I'm just giving you a feel for how some of these additional dimensions identify causal associations, the contrastive or counterfactual explanations, why a prediction was made instead of another prediction, and this is one of the more important ones. If X had not occurred, Y would not have occurred either. And you can think of an example of had you not been smoking, you would not have had that heart attack. So coming up with the driver that caused a prediction to, or a machine learning algorithm to classify you in one way or another, and identifying that in contrastive or counterfactual cases is a very important measure. Then I'm going to, when it comes to interpretability, I'm going to focus on two aspects here. There's a local explanation versus global. And local explanation in the literature is referred to as explaining model characteristics and the impact of input features on the output of a specific example. So in the medical terms, I am explaining why a particular decision was made for a specific patient. I'm not worried about anybody else. It's in your particular case because of your cholesterol measure, because of your heart condition, because of your weight. This is the risk factor that you, patient, have. Global interpretability, on the other hand, is representing the model through the entire data set, through the entire population that you've trained on. So and then the other aspect of this is interpretability being model agnostic versus model specific. Model specific interpretability techniques are tied to a specific class model. So for a decision tree, I am taking advantage of my knowledge of the structure of the tree. For a logistic regression, I am using the coefficients of the variables for the logistic regression. I'm taking advantage of the specific structure of the model to come up with an explanation. Model agnostic explanations, on the other hand, are independent of the internal logic used to generate the prediction. So I'm treating the machine learning model as a black box. I'm only examining the output of that model without any attention to its internal structure, and using the same technique to interpret any machine learning model that I'm trying to evaluate. And in the literature, just giving you a feel for how pervasive these techniques are, I'm seeing a lot more model-specific techniques. So I'm just going to list some here. In trees, interpretable trees for ensemble of decision trees, additive tree models for ensembles of decision trees, feature contributions for random forest classifier, and then for neural net-based algorithms, you get specific explainability methods, such as explainable neural network architecture, deep learning important features, also known as deep lift, reverse time attention retain model as an RNN interpretable, and layer-wise relevance propagation for interpretable deep neural networks. And just for good measures, one more, scalable Bayesian rule list. And what you see here is there is a wide body of literature of people going in and just coming up with methods and explainability techniques that are specific to that algorithm. Model agnostic interpretability techniques are fewer, just because they're fewer in number, but they're actually becoming very pervasive, and there are advantages to having a model agnostic technique. You can have the machine learning algorithm swapped and then evaluated externally as a black box, and take advantage of the most accurate technique that you can get from machine learning prediction, and then explain those techniques with model agnostic methods. So I'm going to list three fairly common and well-established methods here: black box explanation through transparent approximation, SHAP or shapely additive explanations, which is a method that is based on game theory and has theoretical guarantees for coming up with these explanations. And then one of the methods that I'm going to focus on a little bit more is LIME, local interpretable model agnostic explanation. And I'm just going to drill a little bit into LIME and how it works, and just the intuition behind it, to give you a feel for a model agnostic local method. So in this particular area of the diagram, lower left of the slide, you see a decision boundary that is fairly complex. It's this is a classifier attempting to classify red crosses versus blue dots, and the decision boundary is drawn here, and it's fairly nonlinear. And the intuition behind LIME is that it zooms in a particular area in which it's trying to make a decision. In this case, it's this plus red sign, and it's trying to classify it. Is it which side is it on? Is it blue or red? And in this particular case, you would what the LIME method will do is it's going to perturb. It's going to randomly sample around the decision boundary. It's going to come up with its own perturbation method to against the algorithm, and determine where does the particular prediction come up around this decision boundary. And it's going to put more weights in the area closer to this decision boundary, and then wait for decisions that are further apart. And in doing so, it translates or transforms a nonlinear decision model to a linear decision model that it can give a coefficient of explanation for because of the linearity of that model and the simplicity of. And LIME has been used in image classifiers. So you would look at examples where the authors demonstrated how LIME has been providing insight In this case, it was trying to predict wolf versus husky. And what the authors demonstrated through training a biased with bias of data is that wolf was predicted because of the snow in the background. It was not really looking at the particular face of the animal, but it was looking for snow. And anytime there was snow in the background, that was the key to making that prediction. And obviously that's being right for the wrong reason. That's not a predictor that I would trust based on that explanation. In the text analytics domain, they've provided an example of classifying posts as about Christianity versus atheism. And in this particular case, they identified that the classifier had been really overfitting to the noise. It was looking for the domain being edu and words that don't really make sense to be driving the logic of this prediction being about atheism versus Christianity. And with that said, I'm going to just move on to the next area.
Ali,
Yeah.
if I can interrupt you for a short moment. It's just a clarification question. Can you elaborate what local is in the image classifier example?
So in this particular case, it's you can tell it gave us in this image classifier. You can look at where which areas of the image the algorithm or the classifier chose to make its prediction. So this particular case, local was this portion of the face of the husky to come up with a prediction. When it came down to wolf, the local area that it focused on was the image of the snow in the background. Now, had this been a global method, it would have picked the same area of the image for every classifier. But you can see it made a different pick, if you will, depending on that particular image. I don't know if that helps.
Thanks a lot.
Okay. Any other questions?
None at the moment.
Okay, excellent. So one of the areas that is fairly noted in the literature is coming up with an empirical metric for measuring the quality of the explanation. And I'm just going to highlight two attributes cited in the literature, empirically evaluating the quality of the explanation. And they are fidelity and stability. And they are defined fidelity is defined as the level of alignment between the interpretable model and the black box model. You would note that a model agnostic interpretability technique is coming up with its own prediction, and it's essentially a post hoc method that's a surrogate classifier on top of the black box model. So if the surrogate classifier is coming up with classifications that don't represent what's happening in the black box, that's not a useful explanation. I'm just not explaining what's really happening in the black box. And then stability is another measure for local explanation, which is the level of consistency for the same instance. So I'm just going to go back to this particular image and note that to draw up this linear decision boundary, random sampling around it had to take place. So if through this random sampling, I am coming up with different explanations that are widely swinging back and forth for the same instance, that's not a stable explanation, and my level of trust in that explanation is shaken. So these are two empirical metrics used to evaluate the quality of an explanation. Now, and just to give you a feel for how influential Lime is, I'm going to share with you a number of variants of Lime. People have just went ahead and tried to improve on it, and you would notice the date here that this is fairly recent. This is state-of-the-art research that's happening right here and now, and it's part of what makes this an interesting field to look at. So, first variant of Lime that I'm going to share with you is the modified perturbed sampling. It's essentially taking Lime and changing the sampling techniques to consider the correlations between features. So Lime basically does not treats each feature as independent. It's not accounting for the correlation between these features. And this particular study, authors reported that when you consider the correlations between the features, they were able to achieve higher local fidelity than Lime. Then there is K-Lime, which is partitioning of the space using K-clustered partitions to fit a generalized linear model within each cluster. And K-Lime is actually part of the commercial product, the driverless AI by H2O. It's a fairly strong tool, and it's one of the key features that they introduced in that tool is K-Lime. We're able to achieve. Then there is deterministic Lime, substituting the random perturbation with hierarchical clustering to group the data based on K and N to use relevant clusters. And deterministic Lime was reported to improve the stability of Lime because we're not using random sampling, but you're actually coming up with a deterministic reason for drawing up that decision boundary. And as part of the research stream, Rahman Zafar, the author of this paper, is actually going to be joining us in the month of May, presenting this paper and presenting that research. As I'm getting close to wrapping up here, I'm going to just share with you some products, tools, and resources that would be useful to learn about interpretability and just see it being implemented out there in the field. So Sim Machines is a market segmentation company that is using or professes to use machine learning interpretability. FICO, the Fair Isaac Credit report, is has a product called Reason Reporter for fraud detection, and it does use Lime as well. Darwin AI, the company based in Waterloo, they actually recently published a Medium article showing having a proprietary product for interpretability, and they compared it with Lime and SHAP. And driverless AI has a suite of interpretability tools, including K-Lime, Shapley, variable importance decision trees, and partial dependence plots, and a lot more. So those tools are examples, are definitely worth checking out to learn more about this area. With that, I conclude. For those who are interested, just note that all the references on all the studies are available in the slide deck, and I'll be once I share that, this is a good reading list for you to learn more about this area. That concludes my presentation, Suhas, and I'll turn it back to you if there are any questions or comments.
Yeah, thanks a lot, Ali, for your wonderful presentation. I think we had an overview of at least 20 to 30 papers through the course of this talk, I guess. That was a really good overview of all the things that are happening, exciting things that are happening in this space. We have a question from the audience who is Amir is asking, have you looked at IBM F360?
I have not, but I will right after this call.
Mm-hmm. Yeah. And just a question to kick off some discussion. I was wondering what are your thoughts on interpretability with respect to attention mechanisms in recurrent neural networks or transformers, for example. We have seen a lot of papers in recent times about uh, researchers trying to argue that attention means explanation, or and some other researchers showing that it may not be as much of a explainability tool as people think it is. So, what do you think about that?
To be honest with you, that's not an area that I've read a lot about. So I don't have any immediate comment on it. It's not. I need to do more reading on it.
Mm-hmm. Thanks. We have a question from the audience. Do you think there are any approaches in interpretability that allow for coming close to approximating coefficients for black box models? Example, like, yeah, coefficients for linear models, for example.
Well, I mean, if you go back and essentially what line does, it's the explanation of line is provided in the form of coefficients of a linear model. So when line establishes this decision boundary, it's generating a linear model with coefficients that are used for this particular line, and that is the explanation that line is giving you.
Okay. Thanks. So we have a interesting question from the audience. I think, I forgot the name of the paper, but Zachary Lipton had written a nice paper on interpretability and what exactly interpretability means, because there are so many terms here: interpretability, explainability, accountability, and sometimes they are all used to mean the same thing, but they all mean something different, and people conflate them all the time. So the question here is basically, do you agree with the Tim Miller? I haven't read that particular paper, but assumption that research done in the humanities and social sciences should be leveraged to help define interpretability in the interpretable ML field, because I think we are still having a fundamental problem about what exactly interpretability means and what its bounds are.
Yes,
Oh
I
yeah,
mean,
the paper is The Mythos of Model
yes,
Interpretability by Zachary
that's
Lipton.
right.
Yeah.
Okay, then towards the rigorous science of interpretable machine learning. So absolutely, there have been calls. So this paper by Doshi and Kim, one of towards the rigorous science of interpretable machine learning. One of the things that they've called for is more human-based experiments. And there have been examples of user-based experiments where you're comparing the explanation or the answer given by a human expert with what the machine learning explanations are, and seeing the level of alignment. In the line paper, they've had experiments where experimental methods included if can a person look at an explanation and then correct an error of the model by just seeing the obvious, or can a person pick the right model or the better model just by looking at the explanation of that model? So there are examples of human experiments, if you will, to assess machine learning interpretability. But I'm also seeing a parallel track where a lot of these experiments are empirical in nature, and they're trying to come up with empirical evaluations like fidelity and stability to just measure the quote-unquote quality of the explanation. There are there is no one standardized set of definitions. We don't have the same consistency of metrics like we have in accuracy, where you're looking at the F1 score, the specificity, the sensitivity, and the precision of the recall. Those consistent and well-defined metrics that everybody agrees on don't exist for the interpretability world yet. That's why it's an emerging area of research where there's room for people to make contributions.
Mm-hmm. Thanks for the response, Ali. So there is another question from Grant. Line coefficients are specific to individual observations, but what if you want general coefficients for the whole model?
Then you don't use Lime. You use a method that's not for local interpretability, but a global method. So you would, I'll give you an example of a global method that you could use in that particular case. Is you would run a surrogate decision tree. So you would generate a decision tree, and there's a paper out there, I think it was by Leo Breeman, Born Again tree, that demonstrates the usage of surrogate decision tree as the explanation of the black box model. So you would use a method like that, that's giving you a global explanation. And there are other examples that I can point you to. I don't have them with me right now, that offer global explanations of a black box model versus a local explanation.
Thank you. Amir asks, so most models that you talked about are post hoc interpretability techniques. Are there attempts at explanation by design?
Yes. So the methods that, so I am here. So model specifics, and there are actually more model specific explanations than there are model agnostic. So here it is, entries for the ensemble decision trees, additive tree models, feature contributions for random forest, explainable neural network architecture, deep learning important features, deep fit, reverse time attention, retain, LRP, layer-wise relevance propagation for interpretable deep neural network, and scalable Bayesian rules list. So those, I could have easily tripled that list, and there are a lot of people coming up with methods that are designed specifically to work for an underlying model and take advantage of it. Much of the work is geared towards neural networks because they're considered to have higher accuracy, and there's a lot to be gained if those highly accurate models could also be explained.
Thanks, Ali. So I have a slightly non-technical question. So you mentioned earlier in the talk that there are certain sectors, certain industries where there is heavier regulation, where for some decision, if it's made by an automated system, there needs to be an explanation behind what factors were taken into the decision. And given the state of interpretability techniques in machine learning, do any of them even pass the smell test?
Okay, that's a great question, and the answer is we don't know yet. This has not been challenged in court, as far as I know, yet, and there is the right explanation. What exactly does that mean, and does it is it simply being able to trace back how a particular decision was made and preserving the version of the model that was used to make that decision, or is it just giving you the best available information in terms of reason codes in which a particular decision was made? As far as I know, I don't know that these have been challenged in court or been proven in court, but all of these are attempts to comply with these requirements. But whether or not they pass or not, we're just going to have to wait for an actual lawsuit to take place and wait for a legal decision to be made.
Thanks a lot, Ali. So we will be closing down this talk very soon. Does anyone in the audience have any questions? Please comment on the YouTube channel or on Facebook or wherever you are watching. While I wait a minute or two for more questions, I just wanted to let the audience know we have more talks on interpretability on our YouTube channel. If you are interested in BERT interpretability or attention interpretability, we have a couple of videos from back in February. You can scroll down the YouTube channel to find those. And I think, Ali, can you please give a short introduction to the talk that you are organizing at the end of May? You said, I think it's about D-line, right?
Yes. So it's we're very lucky that we were able to host the author for the paper D-line. He is Rahman Khan, and he's affiliated with Ryerson University, and he is we're definitely looking to host him and just have him talk about his paper for deterministic line. That paper has been accepted in KDD, and we're just looking forward to having that presentation and just digging a little bit deeper into that paper and that method that was used and how it compared with Lyme. We could not do that today. Today was more of a broad brush of just the lay of the land and some of the interesting things happening in the field. But when we're going in and presenting a specific paper, we would have an opportunity to dig a little bit deeper and just walk through the method that was used and the results that they generated.
Thanks, Ali. So we have a profound question.
Oh, I like those.
Yeah. So has there been any research on acceptability of explanations? For example, if the reason given is ridiculous, but it's still true, people are going to reject it anyway, right? I mean, yeah.
No, not that I'm aware of, but it would be a great study. Connect with me and let's do it together. I'd love to run that survey and come up with ridiculous explanations and see what the reaction of people would be.
Yeah. Yeah. Okay. Before we close this session, I just wanted to. Yeah. Okay. We have another question. A related question is whether people will even care about explanations if their AI systems work as expected. So let's say there's no regulated industry over here, and we had several Twitter flame wars over this. I remember, because we have some senior scientists in the field who think that, well, we are. I remember a famous scientist whose name I won't take said something along the lines of, "We are not able to explain how flight aircrafts work perfectly, but they still do, and we don't care. So why are you so concerned about interpretability in machine learning models?"
Because this is why you should care. Because according to this neural network, this is a picture of a guitar, and this is a penguin. Mm-hmm. These models can fail spectacularly, and they can fail over silly results. And without those safeguards, without that oversight and human oversight over what these models are doing behind the scenes, they can fail spectacularly. And it is completely okay with me if Netflix recommends a movie that I don't like because their algorithm got it wrong. But I don't know that I would be okay with undergoing a medical procedure based on a machine learning algorithm recommendation if I don't understand the rationale behind it.
Yes. Yeah. So now I think we are ready to close out. But before we leave, I just wanted to announce to our audience that this evening we are having an event at ACE. It's a collaboration with the New York machine learning community, in fact. And it will be about data privacy rights in the age of COVID. There is a panel discussion and breakout sessions over your favorite app, Zoom. So please join in at 6:30 p.m. So Grant Fleming has a comment. Oman Butt and co have done research on how users feel about explanations generated from interpretability methods. So yeah, that's a good paper to look out for. I think we are just about done here. Thanks a lot, Ali. It was a great presentation. Gave us a lot of food for thought, and we hope to see you in May, facilitating this session on DLime.
Thank you, Suhas, and thanks for everybody who attended and shared your thoughts and ideas. And you guys did a lot of homework, a lot of things that I'm going to look up and learn more about. So I appreciate everybody participating in this session. Thank you very much.